Hello, this is Dr. Miller, and I'm going to be going over the pre-lab questions for Lab Activity 3.1. The pre-lab assignment is due October 31st at 4:30. It's a Thursday. So there are 4 questions, and so we'll start with number 1. A student performs a titration by dispensing 24.6 milliliters of 0.10 molarity sodium hydroxide into 35.5 milliliter sample of hydrochloric acid. Calculate the molarity, moles per liter, of the HCl solution. So what we have here is an acid-base reaction, the base being sodium hydroxide and the acid being hydrochloric acid. So we need to think about a balanced chemical reaction first. So what we're getting here, both of these are aqueous. It tells us in water if it's molarity, so it's not and we're supposed to calculate the molarity, so it's an aqueous phase. So what happens is that this ion comes apart like this. So the sodium hydroxide has the sodium ion and the hydroxide ion. So sodium is positively charged and the hydroxide is negatively charged, and that's our base. This is a spectator ion because it's not going to form anything other than being dissolved. The hydrochloric acid breaks up with one of the hydrogens plus the chloride. So this is the acid part, and this is a spectator ion. So these two combine to form water. So H2O plus, and that's going to be in the liquid phase, plus our sodium, and we could write it like this in the aqueous phase, knowing that they really aren't forming a precipitate, they're still dissolved. So that's our balanced chemical reaction. It's a 1-to-1, so for every mole of this we'll react 1 mole of that if we have enough to react. So we're assuming that we have reached the end point. You have to read between the lines on this question. The titration is performed, and there's an indicator that says, okay, now we know that there are equal moles. So whatever moles of this we have this number of moles of that. So I'm going to give you another example, and then you can work through this particular math problem. So let's go and say instead of 24.6 milliliters, we have 25.0 milliliters of sodium hydroxide. And we have, and that's still, let's say, 0.10 molarity. And then we have added to that, let's say, 42 milliliters of HCl of unknown molarity. So we need to figure out how many moles we have of this, and then we'll know how many moles of the HCl we have, and then we can figure molarity. So molarity, abbreviated with a capital M, is moles per liter. So we have, we can figure out how many moles we have because we know how many milliliters we have and what the molarity is. So if we have 0.10 moles per liter, we don't have a whole liter. If we had 1,000 milliliters, we'd have 0.1 moles. But we don't have that much. We have only 25 milliliters. So we need to convert this to liters to figure out how many moles we have. So we're going to multiply that times the amount of liters. We don't have the amount in liters. We could do it in our head and move it over 3 places, or we could do it with our mathematics on our technique here. So we have that many milliliters, and we know that there are 1,000 milliliters in 1 liter. So using that technique, we can cross out the milliliters, we'll cross out the liters, and we'll end up with moles. So using my calculator, which I wouldn't have to if I wanted to do it in my head, but let's do the calculator. We have 0.1 times 25 divided by 1,000. So we have 2.5 times 10 to the negative 3 moles. So the question would be assuming that's how many moles of HCl we have. So that's the amount of moles of NaOH, and because it's a one-to-one chemical reaction, we know that's how many moles of H we have, unless we were told otherwise, and we weren't, of the HCl, I should say. So that's also 2.5 times 10 to the negative 3 moles of HCl. So it asked for the molarity. So we have the moles, and we have the quantity in our sample problem of 42 milliliters. So we need to turn that into liters, milliliters, times 1 liter divided by 1,000 milliliters equals, okay, 42 divided by 1,000, and we know the answer to that is 4.2 times 10 to the negative 2. So that's how many liters we have. So if we have that many moles, we just divide that by the number of liters, 4.2 times 10 to the negative 2. So our answer is 5.95. So that would, sig figs would be 6.0 times 10 to the negative 2. So that's our molarity. Whoops, sorry about that. So 6.0 times 10 to the negative 2. 2.5 times 10 to the negative 2 divided by 4.2 times 10 to the negative 2. Nope, that should be 3. That is a 3. Okay. So that's the answer. That's the sample answer to number 1. So now you need to go and, instead of using 25 milliliters of sodium hydroxide, use 24.6, and instead of 42 milliliters, use 35.5, and calculate the molarity of the HCl solution. So convert molarity to moles, and then find the moles, and then convert that to molarity. So that's number 1. Number 2 is write the balanced equation for the dissolution of potassium hydrogen phthalate, also known as KHP, in water to produce potassium ion and hydrogen phthalate ion. Okay, so this helps to know, it's telling us how it's going to break apart. And another thing that tells us how it's breaking apart is the way they have written the equation, or the molecular formula. They did not write C8H5O4K or KC8H5O4. They wrote KHC8H4O4. That gives us a clue that this breaks apart here and here. So the potassium is going to come apart. So you need to write this as an aqueous solution. So KHCH8H4O4 in aqueous solution dissolves, comes apart. Dissolution means it comes apart. So how it tells us how it's going to come apart. It's going to produce the potassium ion. So you should know by now the potassium ion is positively charged because it's a metal. It's in group 1. So that comes apart like that, aqueous, plus HC8H4O4. And because there's no indication that it's an ion, it's a neutral compound. When it loses that potassium, then it is a negative ion, and so we need to put the negative charge. They have it there, and so that too is aqueous. So I've already given you the answer to this. It's balanced. There's one potassium here, one potassium here, and there's the right number of hydrogens over there. So that's telling us how that comes apart. Now this ion also comes apart in question 3. So now you're going to write a balanced reaction between the sodium hydroxide and hydrogen phthalate ion. So it gives you that. So now, once again, because it's written with one of the H's in front of the rest of it, and this is an ion, this can become dissolved too. It can also break apart. It can just have a dissolution. So the hydrogen is going to come apart and form two negatively charged phthalate ion left over. And that hydrogen is going to react with something in the sodium hydroxide, and I think you probably know by now what that is, how the sodium hydroxide comes apart. The hydroxide, the OH, stays together, and the sodium, of course, is by itself. So then because that breaks apart, just like in question 1, we know that one of those ions is going to react with the hydrogen from the hydrogen phthalate. So go ahead and write that equation. And then, as I said in the first one, that you have spectator ions and you have the base and the acid getting together to form water. The net equation is to not include the spectators because they're not part of the overall change. So we consider just in acid and bases, we consider just the proton and just the hydroxide in the net reaction. So you're going to write this, remember to include the phases, and of course when it's a reaction you have arrows, so don't forget the arrow, and then don't forget the product with its phase. And then of course we know this is an acid, and this is the base, and this is the Arrhenius definition of acids and bases in water, and so it's going to form a product, and you'll need to include that. So that concludes the going over pre-lab questions for lab activity 3.1.